Hello everyone, and today the 5th day of the challenge, Advent of Code. Just to remind you, I'm testing all these problems. We have 25 days. Each day we have 2 problems, and we are testing AI, whether they are able to solve all of them. We are testing Anthropic's Claude 3.5 Haiku and Sonnet, and also we are testing out OpenAI's GPT-4o Mini. We could try later GPT-4o, probably even today, and we have tried O1 Mini. It solved the previous day, only it was able to solve, but we haven't tried the O1 preview yet. But also we can get around these days O1 full model, and we'll see if it will be able to solve all the problems as well, if some of the models will be struggling with. So yeah, let's first read the task. We are, just to remind, we are reading full task. We are just for entertainment, for fun, so it's not for speed, to solve the task for speed. I want to understand the task, and I want to go through the solution that AI will give us. So today is the day 5, print Q.
Satisfied with their search on Ceres, the squadron of scholars suggests subsequently scanning the stationary stacks of Sub-Basement 17. The North Pole printing department is busier than ever this close to Christmas, and while the historians continue their search of this historically significant facility, an elf operating a very familiar printer beckons you over. The elf must recognize you because they waste no time explaining that the new sleigh launch safety manual updates won't print correctly. Failure to update the safety manuals would be dire indeed, so you offer your services. Safety protocols clearly indicate that new pages for the safety manuals must be printed in a very specific order. The notation XYY means that if both page number X and page number Y are to be produced as part of an update, page number X must be printed at some point before page number Y. The elf has for you both the page ordering rules and the pages to produce in each update, your puzzle input, but can't figure out whether each update has the pages in the right order.
All right. So we need to parse some input and to print something else. Sleigh launch safety manual. Okay. For example, we have 47, 53, 97, 13. Then they are divided by commas. And what did it say?
The first section specifies the page ordering rules, 1 per line. The first rule, 47 to 53, means that if an update includes both page number 47 and page number 53, then page number 47 must be printed at some point before page number 53.
At some point.
47 doesn't necessarily need to be immediately before 53. Other pages are allowed to be between them. The second section specifies the page numbers of each update. Because most safety manuals are different, the pages needed in the updates are different too. The first update, 75 from 47 to 61, 53 to 29, means that the update consists of page numbers 75, 47, 61, 53, and 29.
So the second part is what? Some update. Safety manuals are different, pages needed to be different too. All right.
To get the printers going as soon as possible, start by identifying which updates are already in the right order. In the above example, the first update, 75,047, 61, 53, 29 is in the right order.
Okay, I see. So we have the rules here, and we have the not the rules, but the actual ordering, and we need to check whether it is okay, if I understood correctly.
75 is correctly first because there are rules that put each other page after it. 75, 47, 75, 61, 75, 53, and 75, so 29. 47 is correctly second because 75 must be before it, 75 per 47, and every other page must be after it according to 47, 61, 47 to 53, and 47 to 29. 61 is correctly in the middle because 75 and 47 are before it. 75 serves 61 and 47 61, and 53 and 29 are after it. 61 of 53 and 61 29. 53 is correctly fourth because it is before page number 29. 53 tells you 29. 29 is the only page left and so is correctly last.
Yeah, so we have these rules, and we need to store them somehow, and then we need to check all of these numbers if the manual ordering is correct, is according to these rules. Yeah, let's continue.
Because the first update does not include some page numbers, the ordering rules involving those missing page numbers are ignored. The second and third updates are also in the correct order according to the rules. Like the first update, they also do not include every page number, and so only some of the ordering rules apply. Within each update, the ordering rules that involve missing page numbers are not used. The fourth update, 75, 97, 47, 61, 53, is not in the correct order. It would print 75 before 97, which violates the rule 97, 75. The fifth update, 61, 13, 29, is also not in the correct order since it breaks the rule 29, 13.
Yeah, so each of those lines are separate like instructions that we need to check whether they are not violating these rules, all of these rules above. Okay, for some reason, what else? What else?
For some reason, the elves also need to know the middle page number of each update being printed. Because you are currently only printing the correctly ordered updates, you will need to find the middle page number of each correctly ordered update. In the above example, the correctly ordered updates are...
Yeah, we need to determine the middle. Alright, this is clear.
These have middle page numbers of 61, 53, and 29 respectively. Adding these page numbers together gives 143. Of course, you'll need to be careful. The actual list of page ordering rules is bigger and more complicated than the above example. Determine which updates are already in the correct order. What do you get if you add up the middle page number from those correctly ordered updates?
Each puzzle is getting more interesting, and with every day, and I really would like to solve it by myself and then hand it out to the AI, but yeah, I don't think I have much time for that. So let's see what the AI will tell us. I'm working in Cursor, ID, I'm working on the day 5. We have the structure of folders here. We have day 5, we have input, which is currently empty, and we have a solution, which has a template for reading input, part 1, part 2, and to run it. The AI should implement all the parts. I'm attaching a README file which has instructions what this task is about. It's advent of code, and this about the structure and everything. So now I'm attaching a solution of day 5, and I'm attaching the first task. As every day before, how to collapse. we'll be starting from GPT-4o mini, and also I need to attach the puzzle input, which goes to the input.txt. And yep, solve. And let's see what the solution is. Part 1. Rules, updates, data split. Yeah, we have rules and we have then updates. All the rules, tuple, map, int, line split. So we split every rule and we get an integer. Then we get a tuple of integers. Okay. Then we get updates. Again, we split them and make them integers, but now we have a list. Then we get order mapping for xy in order rules, which are those numbers. So xy is first rule and second rule. If x not in order map, then we add it to order map. Okay, so x, because it's previous, like because it should go before that y, we add it there. Then we append y to order map. Okay. I wonder that it doesn't track the y. I'm not sure whether we need to track the y's as well, like their ordering as well. But yeah, we can just try with the x with the first number first. So we get basically from here we get a list of numbers that are sorted, list of rules. So the first column will be sorted from 1 to from min to max. No, is it? No, no, I mean it's not sorted, but this number, it's much more complicated than I thought. Yeah, we have this first column, and for each number we have those numbers, and we add them up. Into a list. Then is ordered. Scene. We create a set. It would be better if GPT-4 Mini wrote more comments for us to understand the code. Okay, so for page in update, yeah, if page in order map, yeah, if the number is in this order map, for after in order map page. So after means next, yeah, all of these numbers that we appended. So we get for after in order map. If after in scene, what is scene, which and false, then we add scene page. Correct updates. We check if they are ordered. Then we get middle page, and then we sum up. From the first glance, should be mostly correct. Not sure if that's fully correct. Day 05. Python source length bin site. Day 05. Python solution 5964. 5964. Yeah, cool. So yeah, GPT-4 Mini nailed this task. I would like to see the solution from Claude 3.5 Haiku, and yeah, and then we'll move on, because I'm pretty sure other models will be able to solve this as well. Not Sonnet, but Haiku. Again, it should analyze the code we have. What? Please. Weird error. Okay, again, what I like about Claude, that it always split the functions into more readable parts, and almost I see it's almost the same code, or just the same code as GPT-4o Mini wrote, but it's split into parsing input is update input. It is an update valid, and it adds the doc strings and comments, so we can actually understand the task. But what I don't like about the code, especially for 3.5 Haiku inside the composer, that it's probably a problem with my prompts, but it's just continues with it tries to close the file and then write an explanation, but it goes not inside the solution file. And I need to manually copy it all the time. But again, it's just a problem with Haiku, because Sonnet handles it fine. Again, we have parsing inputs. Alright, is update valid? Let's see how does it do. For before, after in rules, dependencies, set default. Nice. Oh, create a mapping of which pages must come before others. Yeah, it's like a more advanced approach again, if compared to GPT-4o Mini, but it basically does the same thing. It's a dictionary with a set, and we add into the set these numbers, and then check each page position against its dependencies. For I in page, enumerate if page in dependencies, so if the number inside these dependencies, which are keys, or which are the first number in the first column of the rules. If page in dependency required before, gets which numbers are required before, and then we go for required page in required before, if required page in update in this number, if update index required page. This is harder to read, actually, harder to comprehend. Ensure all required pages are before the current page. I'm not sure I can understand this part from just now. Yeah, valid. Then we get the rules. We get valid middle pages if update is valid. Let's see if we get the same answer. Yeah, fine. All right. I'd like to understand more about this part, but we need to move on to the part 2, and let's see what it's about.
While the elves get to work printing the correctly ordered updates, you have a little time to fix the rest of them. For each of the incorrectly ordered updates, use the page ordering rules to put the page numbers in the right order. For the above example, here are the 3 incorrectly ordered updates and their correct orderings.
So we have 75, 97, 47, 61, 53 becomes 97 switches, swaps with 75, and that's it. Then 29 switches with 13 swaps, and here as well. Okay.
After taking only the incorrectly ordered updates and ordering them correctly, their middle page numbers are 47, 29, and 47. Adding these together produces 123. Find the updates which are not in the correct order. What do you get if you add up the middle page numbers after correctly ordering just those updates?
Okay, we need to we need to find only incorrect updates now, and then we need to sum up after ordering them correctly. We need to sum them, the middle pages, the numbers of middle pages up, and yeah, this one could be trickier. Let's start new composer. Again, attaching readme, attaching solution is already attached. We select GPT-4o Mini and we do this. Okay, correct order, part 2. Let's see, correct order. Create a mapping of which pages must come before others. Sorted update while update, for paging update, if all. Sorted update. So, correct the order is update based on rules. What do we do here? Find incorrectly ordered updates and correct the order. Middle pages for updating updates. If not valid, then we are making it correct, and then we add middle pages which we got from the corrected order. Okay, now we see the correct order. How does it do that? Again, dependence. Oh, no. Oh yeah, this is correct. Dependencies, again, we do the same thing to understand which is correct. Oh no, we just get the rules. I see. Yeah, sorted update, while update, we go for all updates, for paging update, if all, and then we check if all dependencies for this update, for this page, is in sorted update. In sorted update. Okay, so we go for required page in dependencies, get page. Okay. So we get for the selected number, we get all the numbers that should go after it. And then what we do for required page, yeah, we just place them. So if the current update contains these numbers, one of these numbers that should go after, then we do what? Sorted update append page. So we creating a new sorted update, and then we remove it from the current update. We remove it from the update, but update. All right, I see. Interesting. And then we break only if all sorted. I'm not sure whether this is a working version. And it definitely works much longer. I can see my fan is going. I can hear my fan now. Yeah, it should be something that is stuck in a loop or something. If we add logging, probably it won't be. Yeah. I think it is not the correct solution, so it's just stuck in a loop. Or we'll do this very, very long, for a very, very long time. I won't say this is a pass, so we get back to the start, and we try out with Haiku. So please stop that. Okay. By the way, this time Claude Haiku was able to write in a file. And let's see what the solution is about. So part 2, we get the rules, parse input, right, reordered updates, reorder updates for update and updates. If not is valid, we use the same function here. Then we sum up the middle pages. Okay, let's see how it does the reordering thing. So create a mapping of dependencies, the same as before. Create a copy of an update to modify. Okay. Then iterate through each page and check its dependencies. Then we go through the updates for I page in update. For page in dependencies, we go through the dependencies and we get all the numbers that required before. Then find pages that must come before this page. Yeah. So for required in required before, if required in reordered, required for required, required for what? No, for required in required before, we set the list of required pages if it's in the reordered copy. Then move these pages before the current page. For required page, in pages to move, reordered index, reordered remove required page, insert. Okay, just we do the reordering thing. Could work. Yeah. Yeah. 4489. Yeah, it's too low. All right. Yeah. So Claude Haiku, Claude 3.5 Haiku, haven't solved it correctly. We could give it another go. Just Claude 3.5 Haiku. We'll see if the answer will be different. We can submit it as well, but then we'll try Sonnet, then O1 Mini, and then O1 Preview probably. Please do that. Something going on with the cursor today. It just doesn't want me to give me an answer. See, currently it's again part 2 is erased and it's tried to do this, but from what I see, it's just the same code as before. I don't see any changes actually. Yeah, and the answer is the same one. All right, then we are going to try Sonnet. Yeah. We also can try GPT-4o. I forgot about that. Yeah, all right. So this is different. This is definitely different approach. So it creates a graph of a representation of dependencies. This is really nice. I like that. Uses in-degree counting to perform a topological sort. Oh. Handles pages that aren't of any dependency rules. Find invalid updates. Reorder invalid updates. Calculate sum. Alright. I wonder how this works. So part 2, we get the rules, we get middle sums for update and update. If not valid, we get reordering. And let's see, create adjacency list. Wow, graph. We get a dictionary for before, after in rules, before in update for and after in update. So if both numbers are there, we add it to we add both of them to the graph, and we create a set of them, like an empty set. But for the first graph, we add it. We also add to the set we add after. Then initialize in degree counts. In degree node 0 for node in graph. Then we go for node in graph, for neighbor in graph. Node in degree neighbor, in degree get neighbor +1. Topological sort for node in graph if degree node 0 result, while q node q pop result append for neighbor in graph node. Now I'm lost here. I don't know a lot of algorithms, and definitely not this one. I would like to learn it to understand better. Alright, then remaining for x for x in update, if not x in result, extend remaining. So it basically just sorts by the rules and then just adds the remaining numbers if they weren't part of the dependencies of the rules. Could be correct. What was the answer before? It says it was too low, isn't it? Answer is too low. So we should get a higher number, but we get a low one. Ah, no, we get a higher number. All right. Yeah, let's try. Yeah, 1 gold star. Perfect. Super. Yeah, so I'll be analyzing. I could go just in Claude and try to understand if anyone interested, this is what will be doing currently. But I would like to what I would like to do. I would like to submit it, like to commit the changes. Let's do it with the UI. And I'd like to try out the GPT-4o, the larger model, because Mini hasn't solved it. Yeah, the same thing. It uses topological sort. But the code is smaller. Let's see. Reorder update. Create a mapping of which pages must come before others. The same thing. Use a simple insert and sort-like approach to reorder based on dependencies. So get empty order update for page update. Insert position. Insert position land or order update for I in ordered update ordered page. Enumerate ordered update, which is currently empty. If page independencies and ordered page independencies, insert position I. Let's test it. Yeah, it's the same answer, but looks much more clear. Yeah, I think I'll leave it like that, and I'll say I'll try to understand all of these things here with Claude. Again, let's see what image we get here. Oh, all right, we get a smaller version of Christmas tree, because I'd say this is the end of it. We get a reindeer and something I couldn't just get. What is it? What does it look like? Is it a large chimney? Could be this is could be that this is a house, and this is a chimney and a small. But why? What they're doing on the roof? No, I'm not sure what's it. Okay, so the advent of code part ended, and now I would like to understand the topological sort approach. Then I revert back. Yeah. Notice there are two versions of similar code here, with the main difference being reorder update function. I've pasted in both files of generated by Claude Haiku 3.5 Haiku and GPT-4o. What I would like to do. Hi Jarvis. What I need you to do is to help me understand the topological sorting thing here. What is the algorithm applied, and just guide me through this algorithm. I need to really go in depth into understanding of this algorithm. Okay, so, and we can just read it again.
I'll help you understand topological sorting in depth by breaking down the algorithm in the code and explaining how it works. Topological sorting is used when we need to order items based on their dependencies. In this case, ordering pages where some pages must come before others. Let's walk through it step by step. First, let's look at how the dependencies are represented in the code.
Yeah, we have a graph, which is a dictionary, and inside the dictionary we have multiple sets for each number.
This creates a directed graph where each node is a page number, each edge before after means page before must come before page after. Next, we calculate the in degree for each node.
In degree. So yeah, this part what I wasn't able to understand. We have nodes with number 0. It's like initialized, like just initialized empty dictionary. We could also use the default dict here for node in graph, for neighbor in graph node into what? No, I'm not sure I'm able to understand.
The in degree represents how many pages must come before a given page. For example, if page 5 has an in degree of 2, it means 2 other pages must come before page 5. If page 3 has an in degree of 0, it means no pages need to come before it. The actual topological sort.
Okay. So what does it do again? Graph node in degree neighbor in degree get plus 1 in degree neighbor. Zero plus 1. So if it gets inside in degree already, if there is already a number there, we get what? We get the number of pages that go before it. If there is no, we get a 0, and then we add plus 1, like we add 1. Yeah, okay. So the topological sort, Q for node for node in graph, in degree node. So we get Q, which is basically have in degree nodes equal to 0. So this is the first one. Well, Q node Q pop result append for no. Let's see.
Let's break this down with a concrete example. Suppose we have rules 1, 2, 3, 2, 3, 3, 4, meaning page 1 must come before page 3, page 2 must come before page 3, page 3 must come before page 4. The algorithm would work like this.
Okay, so initial state graph 1. So page 1 come before 3, 1, 3, 2 before 3, 2, 3, 3 before 4, 3 before 4, 4, nothing. In degree, all of them have, no. Oh, no. 2, 1 and 2 should come before 3. So we have number 3, and it means that it should have 2 numbers that come before it. And for 4, we have 1. Yeah, probably, because we don't know what comes before it. But something should go, definitely. Because at least this number. Okay, so step 1. Q starts with nodes having in degree 0, 1 and 2. Meaning they should come, nothing comes before them. Result. Step 2, take 1 from Q. Result 1. Decrease in degree of 3. No 1. Decrease in degree of 3. Why? Okay, so we have a Q. Oh, Q is 1, 2. Okay, take 1 from Q. Result 1. Decrease the degree of 3. Okay, after we popping out, we decrease the degree of 3. No 1. Then we take 2 from Q. Again, we get result 1 and 2. Because they should go before 3. They have in degree 0. Decrease the in degree of 3. Okay, now nothing comes before 3. And then we can add... and then we add 3 to the Q. Since its in degree is 0 now. Step 4, take 3 from the Q. Yeah, this is the next step. Result, we get this Q. In degree of 4 is decreasing because we get 3. Because it was its dependency. And then adding 4 to the Q. And there we're done. Cool. So what's next?
The key insights of this algorithm are: it always starts with nodes that have no dependencies in degree each 0. As we process each node, we remove it from the graph by decreasing the in-degree of its neighbors. When a node's in-degree reaches 0, all its dependencies have been satisfied, so it can be added to the queue. If there's a cycle in the dependencies, some nodes will never reach in degree x or 0, and the queue will empty before processing all nodes.
Not sure I understood this one. Probably just if there is a cycle, if the input is incorrect. Finally, code handles pages that aren't part of any dependencies. Yeah, we understand that. Algorithms has several advantages. Let's see what are them.
This algorithm has several advantages. It's efficient. OV plus E, where V is the number of nodes and E is the number of edges. It detects cycles implicitly, if result length, number of nodes with dependencies. It produces a valid ordering if one exists. Would you like me to elaborate on any part of this explanation or show how it works with a different example?
No, I think I understood now. Let's go again. So in degree node, for node in graph, for neighbor in graph, in degree neighbor, we get this in degree or 0 plus 1. Then we get a queue, which are for in degrees equals to 0. Then we go through the queue. But we're not iterating like with a for loop. We are just, what do we do? Yeah, we just empty it out. Result. And we add to the result. So for example, we added 1. Then we go for neighbor in graph node. What does it mean? Node. So we got here 1. Then we got all the numbers that should go after 1. We decrease the in degree of those neighbors. And then if degree of neighbor, we add if degree in degree of neighbor is 0, we add it to the queue. Then the queue is empty, and then we add the remaining. Not sure if I am able to repeat it by myself, but yeah, I could try that later. I like that I learned something new today. Alright, so yeah, this is it for the 5th day. Let's see you on the 6th day, tomorrow, probably the same time as today. I will just post it's on YouTube, like create a live, currently schedule the live stream currently right now. Thank you for watching, and please leave a like if you watched until this moment. Thank you.